Greetings everyone to the second video in this 10 video series. My name is Vyom Khanna and I'm delighted to be with you here today. In the previous video, you learnt about the Internet of Things and how it can be used in your daily lives. Over the course of the next few videos, you will learn about Arduino, soldering, sensors, Node MCU and their real-life applications. So get ready and let's get started. Today, we are on the second video in this series, so get ready to take it up a notch. In this video, we will dive deep into the concept of microcontrollers using a simple LED demonstration. We explored the advantages and disadvantages of the Internet of Things, and we ended the last video with a discussion on the components of IoT. You may remember the word microcontroller, one of the components used in building an IoT system. If you remember correctly, you would recall that it is the so-called brain of the IoT system. In formal terms, a microcontroller is a compact, integrated circuit used to govern and control a specific task in a system. Typically, microcontrollers include processors, memory, input and output ports on a single chip. It is the fact that all of the features are available on a chip that makes microcontrollers so powerful. Microcontrollers are present in vehicles, robots, office machines, radios, vending machines, home appliances, and many other places. To explain in the simplest way possible, microcontrollers are just mini computers which are used to control simple tasks in an extensive system. They are much less complex than computers as they do not need a front-end operating system. A microcontroller is embedded inside a system to control a particular function in a device. It does this by interpreting data it receives from its input-output peripherals using its central processor. The temporary information that the microcontroller receives is stored in its data memory, where the processor uses instructions stored in its program memory to decipher and work with the incoming data. It then uses its I/O or input and output peripherals to communicate and enact the appropriate action. Microcontrollers are present in a wide array of systems and devices. Devices often utilize multiple microcontrollers that work together within the device to handle their respective tasks. For example, a car might have many microcontrollers that control various individual systems, such as the anti-lock braking system, traction control, fuel injection, or suspension control. All the microcontrollers communicate with each other to inform the correct actions. Some might speak with a more complex central computer within the car, and others might only communicate with other microcontrollers. They send and receive digital data using their I/O peripherals and processes it to perform their designated tasks. Now that you've understood the basic idea of what microcontrollers are and how we can use them, why don't we shift the discussion to anatomy? If you plan to work with microcontrollers in the future, you will 100% need to be familiar with their principles and individual parts. So let's get familiar with some of the core elements of microcontrollers. The processor. A processor is like the brain of the microcontroller, and it processes and responds to various instructions given by the user. Thus, the user can provide specific commands to the microcontroller, just like a software program. In this way, microcontrollers are a beautiful intersection between the digital and physical spheres of technology. The majority of basic instructions involve performing the basic arithmetic, logic, and I/O operations. Using instructions, we can also get the microcontroller to perform data transfer operations, which communicate other commands to other components in more extensive embedded systems. A microcontroller's memory stores the data that the processor receives and uses it to respond to instructions that it's been programmed to carry out. A microcontroller has two main memory types. Be sure to note the differences between the two memory types. Firstly, program memory. It stores long-term information about the instructions that the CPU carries out. Program memory is non-volatile memory, meaning it holds information over time without needing a power source. This type of memory is like the ROM or read-only memory, which we regularly see on personal computers and laptops. Next, there is data memory. This is required for temporary data storage while the instructions are being executed. Data memory is volatile, meaning that the data it holds is temporary and is only maintained if the device is connected to a power source. Data memory is like RAM or random access memory, which I'm sure you have heard countless times if you are familiar with tech specs. Lastly, there are input-output or just simply I/O peripherals. The input and output devices are the interfaces for the processor to the outside world. The input ports receive information and send it to the processor in binary data. The processor gets that data and sends the necessary instructions to output devices that execute tasks external to the microcontroller. We can exploit these input and output features of a microcontroller by connecting it with sensors, which involve the input function. Then, we can send this data from the sensors to other places, even computers. This quote-unquote sending of data consists of the output function. While the processor, memory, and I/O peripherals are the defining elements of the microprocessor, other factors can also be present. I/O peripherals refer to the supporting components that interface with the memory and processor, and many supporting components can be classified as peripherals. Having an I/O peripheral is absolutely necessary for a microcontroller. Generally, microcontrollers are designed to be readily usable without additional computing components. They are designed with sufficient onboard memory and offer pins for general I/O operations to directly interface with sensors and other components. They do not require any complex supplements or heavy power sources to operate, and they are easily implementable and user-friendly. Now that you know the fundamentals of microcontrollers and exactly how they operate, it's time to clear up some common misconceptions. In technology, especially the IoT sphere, you will have heard a great deal about microcontrollers and microprocessors. You may have already confused one term for another, even though there is a significant distinction between the two. Well, let me clear it up for you. A microprocessor is a single integrated chip that contains a device's CPU. However, it does not include any RAM or ROM memory or other peripherals that a device may have. Instead, the chip relies on input or output to connect to memory and peripherals. On the other hand, a microcontroller has the CPU, RAM, ROM, and peripherals embedded onto a single chip, which effectively makes it a computer on only one chip. As we progress along with the video, you will see the true all-in-one character of microcontrollers and will be blown away by the example of the Arduino UNO. With everything embedded on a single chip, a microcontroller has lower performance capabilities than a microprocessor-powered computer. However, when it comes to typical IoT devices, such as smart home appliances, microcontrollers are much better, and they do provide sufficient computing power while keeping costs and complexity low. There are so many types of microcontrollers in every tech market around the globe. How do you choose which one you want? Read on to see how to make an educated and informed decision. The first factor to consider while making your choice is memory. The amount of memory you choose will of course have a fundamental impact on the device's overall performance. Therefore, carefully calculate the memory requirements of your device's programming tasks, both the RAM and the ROM. You also need to ensure that you future-proof your decision by having enough spare capacity to handle the demands placed on it by future updates. Make sure you don't buy a model that the manufacturer has already discontinued. You want to buy something relatively new and relatively popular, as you can guarantee that it will have support for external devices. Your device's power requirements are another primary consideration when choosing the best unit. An intelligent IoT biomedical device will run on a low power battery. In contrast to this, heavy, innovative industrial equipment will consume a lot of electricity, but you'll want the device to be energy efficient. So, depending on the motive of your IoT system, the power supply of the main board will play a significant role. How will your IoT device connect to the application? What type of data will the device be pushing? And where? Does it need to interact with other devices locally? For example, a residential alarm system may need Wi-Fi protocols, while an office ventilation system may require a wired Ethernet connection. The device may require a Bluetooth connection or even Wi-Fi. So you need to make sure the microcontroller you purchase supports the desired mode of transfer of information, be it wired, Bluetooth, Wi-Fi, or even something else. The next factor to consider is connection ports. To work out how many input and output ports you need on your microcontroller, you first need to know what data inputs your device requires. Also, bear in mind there are both digital and analog ports on the usual board, which process different types of data input and outputs. I know what you're thinking right now. Enough talk about the theory and build of a microcontroller. Can't we see some real-life examples and actual models? I know the theory of a microcontroller and anatomy may have been rather tedious. Still, if you want to study further in the IoT field, with gazillions and gazillions of new topics and sensors, you will need to remember the basics. If you lose touch with your basics, you will be lost, and it will be hard for you to explore the new topics without having a solid foundation. So let's get started. One of the most popular microcontrollers is the Arduino UNO. It is a low-cost, flexible, and easy-to-use programmable open-source microcontroller that you can integrate into various electronic projects. This board can be interfaced with other Arduino boards, Arduino Shields, and Raspberry Pi boards, and can control relays, LEDs, servo motors, and so much more. Throughout our videos, we will be using the Arduino UNO as the main microcontroller because of its simplicity and user-friendliness. Arduino UNO is easy to program, and a person with little or no technical knowledge can get hands-on experience with this board. The Arduino UNO board is programmed using Arduino IDE software, an official software introduced by the Arduino company. The Arduino program is initially called a sketch, which you need to upload into the board. The sketch is nothing but a set of instructions that allow the board to perform certain functions as per your requirements. Keep this information in mind as we will delve deep into the Arduino coding language and how to give instructions to a microcontroller in the following video. Now, you should have gained a magnificent understanding of the Arduino UNO board and the microcontrollers. You know how, why, where, and when to use a microcontroller. But before we move on, there is one more topic that we must tackle. Here, we explore the advantages of Arduino boards compared to the traditional microcontroller. Arduino boards can perform some functions, but almost everyone prefers the Arduino board over the microcontroller. Why? Well, it's because Arduino boards are easy to use. You don't require a lot of expertise to run them. Plug the board into the computer and you're ready to start playing with it. Moreover, while using Arduino boards, you don't require extra peripherals and components to run the boards. Arduino is the complete board that comes with GPIO pins, analog pins, and a microcontroller as the heart of the board. On the other hand, a traditional microcontroller is a chip where all the necessary parts like the microprocessor, RAM, and flash memory are incorporated into a single chip. That concludes our discussion on microcontrollers. Now, let's focus on the other essential parts of a traditional Internet of Things circuit. What does the microcontroller connect to? Read on to find out. One crucial component is the breadboard, the bread and butter of DIY electronics. Breadboards allow beginners to get acquainted with circuits without soldering, and even seasoned tinkerers use breadboards as starting points for large-scale projects. A breadboard is a simple device designed to let you create circuits without the need for soldering. They come in various sizes, and their design can vary. But as a general rule, they look something like this. If you've never seen one before, you might wonder how to tell which holes do what. It becomes easier to understand what's going on when you see one from the bottom. Seeing it from this perspective makes it easier to understand what is going on. The two larger pieces of wire down each side connect to power sources to the board, referred to as power rails. The other smaller pieces of wire running vertically across the board are used for the components in your circuit. This diagram will help visualize the pattern from the top. The power rails run horizontally in two rows at the bottom and the top. Meanwhile, the vertical columns run inwards as you move down the board. If you were to pull any of these metal pieces out, you would see their purpose. They're designed to grab onto the legs of any component that's pushed through the breadboard holes. This feature allows you to test circuits without worrying about soldering or making good contact with the board. As a general rule, this is how all breadboards operate, though they can come in various sizes. Some breadboards have binding posts to attach to a power supply, but you can get by just fine without them. Also, most breadboards are designed to clip together if you need loads of room for a mega project. Basically, breadboards are used as joint power sockets, acting as a common base for almost every component in the circuit. Next, we move on to the discussion of jumper wires, which are simply wires that have connector pins at each end, allowing them to be used to connect 2 points without soldering. Jumper wires are typically used with breadboards and other prototyping tools to make it easy to change a circuit as needed. It's relatively simple, and in fact, it doesn't get much more basic than jumper wires. Though they come in various colors, the colors don't really mean anything. This means that a red jumper wire is technically the same as a black one, but you can use the colors to your advantage to differentiate between the types of connections, such as ground or power. Jumper wires typically come in three versions: male to female, and female to female. The difference between each is in the endpoints of the wire. Male ends have a pin protruding and can plug into things, while female ends do not and are used to plug things into. Male to male jumper wires are the most common and what you will likely find you use most often. When connecting two ports on a breadboard, a male to male wire is what you will need. Make sure you become proficient with the use of jumper wires. Throughout this video series, and even your IoT journey, everything will change. The microcontroller, software language, etc. are always prone to change. However, at least in the near future, jumper wires are here to stay. They are instrumental in color coding and organizing, apart from obviously connecting two things. So keep your eyes open. Next, let's briefly talk about how we plan on communicating our instructions to the microcontroller. We do this by coding software on our computers. But where exactly? For Arduino boards, we use the Arduino IDE. It is open source software designed by the Arduino company, and it's mainly used for writing, compiling, and uploading code to almost all Arduino modules. It is an official Arduino software, making code compilation so easy that even an ordinary person with no prior technical knowledge can get their feet wet with the learning process. It's available for all operating systems, that is Mac, Windows, and Linux, and it even runs on the Java platform. It comes with inbuilt functions and commands that play a vital role in debugging, editing, and compiling the code. A range of Arduino modules is available, including Arduino UNO, Arduino Mega, Arduino Leonardo, Arduino Micro, and so many more. Each of them contains a microcontroller on the board that is programmed and accepts the information as code. The main code, also known as a sketch, which is created on the Arduino IDE platform, will ultimately generate a hex file, which is then transferred and uploaded to the controller on the board. The IDE environment mainly consists of two essential parts: the editor and the compiler. The former is used to write the required code, and later and the latter is used to compile and upload the code into the given Arduino module. This environment also supports both C and C++ languages. The IDE is a potent tool, and if you've mastered it, then you can make Arduino IoT systems perform almost anything you want. Stay tuned for the following video to delve deep into the inner workings of Arduino code, the language rules, and what we can do with it. As the last topic today, let's see a small demonstration of the Arduino's power. This is perhaps the simplest demonstration out there, consisting of an Arduino UNO, jumper wires, a breadboard, a resistor, and some LEDs. Over here, you can see that there are two jumper wires connected from the Arduino UNO to the breadboard, which are used to make this LED periodically blink. I hope you've enjoyed yourself and gained a concrete understanding about Arduino and microcontrollers. I'm looking forward to being with you in the third video. So until then, bye.